Alright, welcome to the video on factoring quadratics using the AC method and the difference of squares. We're going to start with example 1a, which is a quadratic with a leading coefficient that is not 1. The process for which we go through this is first we're going to check to see if it's factorable, and so we look at what's called the discriminant, b squared minus 4ac, and we check to see if it's a perfect square. So the b value is -7, the a value is 3, and the c value is -6. If b squared minus 4ac is a perfect square, then the expression is factorable. And that's a nice check to do before you start your problem. When we go about factoring using the AC method, what we're going to do is we're going to look at what is the product of a and c. So in this case, 3 and -6 is -18. And what is the value of b? -7. And we want to find two numbers that multiply to -18 and add to -7. So I'm looking for these two numbers, and I come up with -9 times 2 is -18, and -9 plus 2 is -7. This allows us to split the middle term into two separate terms with those as the coefficients, -9x and 2x. Now that we've taken our quadratic and split the middle term, we have a 4-term polynomial expression, and we can factor by grouping. And the way that works is we look at the first two numbers, or first two terms I should say, and see if there is a common term that comes out of those first two terms. And there is. It is a 3x. 3x times x is 3x squared, and 3x times -3 is -9x. After we've done that for the first two terms, we'll repeat the process for the second two terms. And the common term that can pull out of the second two terms is a +2. So we pull a +2 out, and we're left with x minus 3. +2 times x is 2x. +2 times -3 is -x. Then we factor the x minus 3 to the front of the expression. So if I pull an x minus 3 out of the first term, I have a 3x. If I pull an x minus 3 out of the second term, I have a +2. So x minus 3 and 3x plus 2. This is our final factored expression. We should double check to see that there's no additional numbers that we can pull out. 1 and -3 are relatively prime, 3 and 2 are relatively prime, so we're good. That's example 1a. Okay, let's look at example 1b. Here's a quadratic. First things first, I check to make sure that the discriminant is a perfect square. 64 is 8 squared, so we're good. Then I'm going to look for two numbers that multiply to 20 and add up to 12. 2 times 10 is 20. 2 plus 10 is 12. I split the middle term. That 12x became 2x and 10x. And then I'm going to factor the greatest common factor of the first two terms and the greatest common factor of the second two terms. So 2x comes out of both of those, leaving behind 2x plus 1, and 5 comes out of both of these, leaving behind 2x plus 1. You would know that you're on the right track if your parentheses match. And since these two parenthesis sets match, we're on the right track. We can pull that parenthesis to the front, leaving behind a 2x and a +5. And of course, we check to see if there's any additional terms that can be pulled out, and there is not. So we're good there. Okay, we're going to look at example 1c, and in this, it doesn't immediately look like a quadratic. However, if you note that x to the 4th is x squared squared, what we really do have is a quadratic. It's just that our powers have been squared. So we still can apply the AC method to this approach. We're going to check to see that our discriminant is a perfect square. it is, so everything's good there. We're looking for two numbers that multiply to 36 and add to 12. 6 times 6 is 36. 6 plus 6 is 12. So our middle term can be split. 4x to the fourth. The 12x squared becomes 6x squared and 6x squared. Then we're going to factor out a common factor of the first two terms and a common factor of the second two terms. And we arrive at common parentheses. So we're on the right track. We pull that common parenthesis to the front and we get this expression. Now, some students might combine this, which is acceptable. They could write this as 2x squared plus 3 squared because it is the same term. And on top of that, some students have a formula that they consult when they see a very specific form, which I'll show you now. It's not one that I spend a lot of time talking about, but it is a way you could approach this problem. If you have the foresight to recognize that this quadratic is of the form term squared plus 2 first term, second term, and second term squared. So recognizing this form, some students can move to here because this is a common form for polynomials. Our first term in this case was 2x squared squared, and our third term was 3 squared. And so is 2x squared times 3 times 2 our middle term? And it is. I don't spend time diving into this approach because I like the idea that the AC method will always work, and so let's use the approach that always works. This is a special case. All right, let's look at example 1D. 1D. We're going to check to see that this is a perfect square. 216, if we try to square root that, we find that 216 is not a perfect square, so this function, g of x, cannot be factored. So we don't even have to start doing the AC process because we've proven to ourselves that 216 is not a perfect square. The discriminant is not a perfect square. So this is a prime polynomial. It cannot be factored any further than it is, at least with real numbers. With rational answers. So if we wanted to actually find the zeros of the function, we could rely on the quadratic formula for that purpose. So in my class, when you get to an expression that is not factorable, this is the approach that I want you to take. I want you to show me that you know it's not factorable before you write prime as an answer. Okay, let's move on to example 2. In example 2, we have a quadratic that has a greatest common factor. We should always look for those first. So since all of these numbers were even, I was able to factor out a 2. Now please note the 2 doesn't disappear, it just moves to the front. Now I'm going to run the discriminant on what's left. The discriminant is equal to 16, which is a perfect square, so I know that this quadratic can be factored. I look for two numbers that multiply to 60 and add up to negative 16. We're going to split the middle term so that negative 16 becomes negative 10 and negative 6. Then we'll find the greatest common factor of the first two terms and the greatest common factor of the second two terms. And then our parentheses match, so that's a good sign that we're on the right track. And we get to our destination. Do one last check to make sure that there's nothing else that can be factored, and all looks good. So there we have it. Example 2b. This is a difference of squares, and I'm going to show you the difference of squares method after I show you the AC method on this. So the AC method, first we check the discriminant, it's a perfect square, so the expression can be factored. We need numbers that multiply to negative 100 and add up to 0. So that's negative 10 and positive 10. So we'll split that middle term, which is 0x, into the two terms, negative 10x and positive 10x. Then we pull out a common factor of the first two terms, common factor of the second two terms, and we arrive at our destination of a factored form. Now, this particular polynomial is of the form a squared minus b squared, where a is 2x and b is 5. So 2x times 2x is 4x squared, and 5 times 5 is 25. So in the event that you see this form, you can apply what's called the difference of squares. And the difference of squares is a much faster method where we know that the expression is going to factor into a minus b times a plus b. So we can write that out. Our a value is 2x, our b value is 5, and then our a value is 2x and our b value is 5. So knowing the difference of squares approach will save us time when there is no middle term in our quadratic, if this is in fact a difference of squares, which it is. So I'd recommend actually learning that approach, and my experience with students is a lot of them are pretty good at recognizing this. Just note that it has to be a subtract. If it's a addition between these two things, there's nothing we can do that looks like this for difference of squares. So, okay, let's move on to example 2c. We have another quadratic here. Note that the middle term, x squared, if we square that, we get x to the fourth. So we do have a quadratic. Your middle variable squared should be your first term. Check the discriminant. It equals 0, which is a perfect square. We're going to look for numbers that multiply to 12, to 36, and add to 12. You can split that up. And I think this problem was actually the exact same problem that we just did. Whoops. I forgot to change a problem. Example 2c and example 1c are the same problem. Well, it doesn't hurt to do it twice. In one of my math classes, I did some of my homework assignments 2 or 3 times just to develop the skill. So factoring is a skill that doesn't go away, so extra practice is never harmful. Okay, let's look at example 2d. We have a negative leading coefficient, so I'm going to go ahead and factor a negative 1 out. It doesn't look like there's anything else that can factor, so there's our greatest common factor. Then I'll check the discriminant. b squared minus 4ac is 496, which I don't think has a perfect square. If I use my calculator, yeah, nope, there's no square root for 496. That's an integer. So since 496 is not a perfect square, the function cannot be factored any further. So we'll leave it at that, negative 1 times that expression. I don't exactly want to say that it's prime because we can pull a negative 1 to the front. So I like to have my a value as a positive number when I factor my expressions. And like all quadratics, you can also find the zeros of quadratics using the quadratic formula. Because our discriminant's a positive number, we know that there are 2 real roots for this polynomial. All right, that's going to be part 1 for the video. Check back soon for part 2 where I walk through some more examples, but this probably should suffice for most people. Thanks for watching. Be sure to comment, like, subscribe, hit that bell for notifications, and have a good day.